Welcome to Maths with EJD. We are talking about numerical analysis, and in the last three videos, I think we've been talking about, I think four now, we've been talking about nonlinear root finding methods. Okay, non-linear roots, or rather, we are looking for the roots of nonlinear equations. So let me just say nonlinear roots finding, and we have identified two major types of kinds of methods to solve them, to find these roots. We have 2-point methods where we need values within an interval, or we need two initial guesses. So we need an interval, like in the case of bisection, or we need two initial guesses, like in the case of second method. So we also have 1-point methods. We have 1-point methods like uh, 1-point method like fixed point iteration, and then we have another 1-point method like Newton-Raphson. Why they are 1-point method is because they require an initial guess for us to find the roots. So far we have dealt with bisection, we have dealt with seconds, we have dealt with fixed point iteration. Now we are looking to deal with Newton-Raphson. So let's look at the Newton-Raphson method and see how it compares with the other methods. Newton-Raphson method. Okay, so the Newton-Raphson method, the Newton-Raphson method is a powerful technique that uses both function value, both function value and its derivative, and its derivative both so we need the function and its derivative to iteratively approach the root. Approach the root. Okay. It is known for its fast convergence, especially when the initial guess is close to the actual root. Okay. Now let's look at some steps that we need to take. So look at steps in Newton-Raphson method. Newton-Raphson method. Okay, so the first step is just choose an initial guess. Choose an initial guess. That's why it's the 1-point method. Choose an initial guess x naught to apply the Newton-Raphson iteration formula. And what is that? The Newton-Raphson iteration formula is simply this: xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So that's why we need the function itself, and we need the derivative of the function. So that is the Newton-Raphson iteration formula. So it's really the key here. Of course, we know the stopping criterion. The stopping criterion is to evaluate. That's step 3 now. Repeat process until the absolute value of f of xn plus 1 is less than the tolerance limit. It's less than epsilon, where epsilon is equal to tolerance limit. Tolerance limit. So that's how we go. So, I mean, so far we have seen that we can check tolerance limits in 2 ways. We can actually use, I think I've mentioned this previously. So generally, tolerance limits, either you check xn plus 1 minus xn is less than epsilon, or you check absolute value of f of xn plus 1 is less than epsilon. So those are the 2 possibilities you can adopt to check for the stopping criteria. All right, so having said that, can we then go ahead and solve the same problem we've been solving from the very beginning? So the question, so we have the example here. Find the roots, or roots, if possible, of f of x equals x cubed minus x minus 2, given initial guess. So the initial guess will determine how fast you move, how fast you reach the answer. Given the initial guess, x naught equals 1, and tolerance limit, epsilon equals 0.01. Okay, that's what we have to deal with now. So let's go for the solution. Again, we outline the things we have. F of x equals x cubed minus x minus 1. Okay. Well, I think let me start with the formula, right? Let's start with the formula. The formula tells us that xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So we need the derivative at every point in time. So what are the things we have? We have f of x to be x cubed minus x minus 2, I think, minus 2, right? Yeah, minus 2. So, and we need the derivative, so we could as well get that straight. So f prime of x is equal to 3x squared minus 1. So if we differentiate this is what we get. So what else do we have? We have the initial guess, x naught to be 1. Then we have the tolerance limit to be 0.01. So these are the resources we have to work with. So can we start the iteration? The first iteration, we are going to have x1. That's when you set n to 0. So if you set n to 0, so we have x1 equals x naught minus f of x naught over f prime of x naught. So that's x naught minus f of x naught divided by f prime of x naught. Okay, so that tells us that we have x1 to be x naught is 1 minus f of x naught. That's x cubed. That is 1 cubed minus 1 minus 2 all over 3 of x. That's 3 1 squared minus 1, like this. That's just substituting that x naught into this. So 1 cubed minus 1 minus 2, 3 1 squared minus 1. That's what we have down there. So that means that x1 is equal to 1 minus 1 raised to power 3. That's 1 minus 1 minus 2 all over 1 raised to power 2 is 1 times 3 minus 1. So that x1 is equal to 1 minus 1 is 0, 0 minus 2, that's minus 2 all over 2, like that. So that x1 is equal to minus 1 minus, that's minus 1 minus minus 1 That's 1 minus minus 1. So that x1 is equal to 2. In short, x1 is equal to 2. So we have our x1 to be 2. So what we are going to do next is to see the convergence criterion. So we need to check if what does f of x1 look like. Okay, f of x1. So f of x1 means absolute value of now we have got x1, right? So that would be 2 cube minus 2 minus 2, like this. So this is absolute value of 8. Let me bring that down for easy handling. So that is absolute value of 8 minus 2 minus 2. So that's absolute value of 4. And that is 4. So 4 is greater than 0 0.01. So what does that mean? It means that iteration continues. Iteration continues. And don't forget, we have got don't forget whatever this value is. 8 minus 2 minus 2 is 4, because we are going to need it for the next iteration. Okay. So the next iteration now, we need x2. Okay. So we have x2 equals x1 minus f of x1 divided by f prime of x1. So we already know f of x1. Don't forget, it's this 4. So we don't have to stress about that again. So x2 now is equal to x1 that we got was 2. So this is 2 minus f of x1 is 4 divided by f prime of x1 now. So that our x1 is 2. So f prime is 3x squared minus 1. So that is 2 squared minus 1, because x1 is actually 2. So we do that again. So x2 is equal to 2 minus 4 all over 2 raised to power 2 is 4 times 3, 12 minus 1, that's 11. 2 minus 4 over 11. 2 minus 4 over 11. So we can find the LCM. So x2 is equal to 11. That's 22 minus 4, which is 18 divided by 11. We can leave it like this, or we can do the decimal. That's 1.636364. Okay. So, I mean, anyhow we want it. But let me go for the decimal. X2 is 1.636364. And we have this as x2. So the next thing is to check if we have arrived or not. So we need absolute value of f of x2. Absolute value of f of x2. And for the absolute value of f of x2, we need absolute value of I mean, the decimal might be convenient in this case. So we have 18 over 11. I mean, the fraction, right? 18 over 11 cube minus 18 over 11 minus 2. That's like x cube minus x minus 2. And this gives us the absolute value of 0.745304. So watch out, because this is our f of x2, which we need later. This is simply 0.745304. And this is still greater than 0.01. So what happens? Iteration continues. Iteration continues. Okay. Now we go for the next one. We now go for x3. And we know that x3 is equal to x2 minus f of x2 divided by f prime of x2. So we know x2 already. So x3 now is equal to x2. We know x2 to be 1.636364. So 1.636364 minus okay. I mean, fraction seems more beautiful here. At least we can still use fraction. So let's just go for that. So it's the same as 18 over 11 minus f of x2, which we already got to be 0.745304. We have that all over. This is 3x squared minus, and that's 3 into 11. I mean, 3 into 18 over 11 squared minus 1. So that x3 is equal to 1.530, 1.530.392. So we have that. So again, we need to check, have we arrived? How do we check? Which we need f of x3. We need f of x3. So f of x3 simply means that we have 1.530392 cube minus 1.530392, all that minus 2. And that will be absolute value of f of x3 to f of x3 actually, and that is 0.053939. Okay, that's where we are at now. I mean, we are hopeful because the values are, it's reducing 0.053939. This is still greater than 0.01, but we are hopeful because it's going. So it's reducing. So iteration continues. So probably in one or two iterations, we'll be fine. Iteration continues. So we can move to the next one where we have we can go for x4 now. So x4 is equal to x3 minus f of x3 all over f prime of x3. Don't forget that we already found f of x3, which is this expression here. So you can just import that in here. So x4 is equal to x3. x3 itself is 1.530392. 1.530392 minus f of x3, which we found up there, that's 0.05. So that's 0.053939 divided by f prime of x3. So that is 3 into 1.530392 squared minus 1. So if we simplify all that, so our x4 would be 1.521441. So that is our x4. So let's check if we have arrived or not. Are we there yet? Let's see. So we do absolute value of f of x4, which is absolute value of x4 is that now. So we have 1.521441 raised to power 3 minus 1.521441 minus 2. So that is absolute value of 0.000364. Now this is convincingly there. So this is 0.000364. This is clearly less than 0.01. So therefore, the solution has been reached. The solution has been reached. And it is x4, okay? This is x4 equals 1.521441. 1.521441. As such, the solution to f of x equals x cubed minus x minus 2 using Newton-Raphson method, with initial guess. You know, those conditions are important. With initial guess, x naught equals 1 and tolerance limits epsilon equals 0.01 is x equals 1.521441. Now, I mean, this is 3 iterations and we've arrived at the answer. Okay, in the next video, definitely, I want to compare, I'll be talking about the comparison between the 3 methods. So let's look at the code for Newton-Raphson in this case now. Right? Newton-Raphson, yeah, this is what this looks like. So view, show line numbers, all right? So here, I mean, we have everything. So we have the function f of x, then we have its derivative, and of course, you can study the code to see how it goes. I mean, for some weird reason, I'm not able to use angle brackets or something like that in the YouTube description box. But if you can check on Facebook, you can find the code right there. Okay. So I mean, if I run this now, I mean, in fact, in one blow, it just does it straight. Oh, here because the initial guess is 1.5. So if I make it one, it's a bit slower. So you can see with 1.5, you need just like one iteration. But if I make it one, so I did it like in 3 or 4 iterations. Yeah, 4 iterations, like you can see up there. So that's what Newton-Raphson looks like. Thank you so much for listening. So if you have not subscribed to this channel, if you have subscribed, let me start with that. If you have subscribed, thank you for doing that. If you haven't, please go ahead and do that right now and hit the notification bell so you can always get alerted each time a new video is released. Um, you know, in the next video, I'll be comparing all the methods, just talking about their strengths and weaknesses, basically. And then if you have not, if you have a comment, like you want to tell me how helpful these videos are, please go ahead and let me know. And apart from that, let me know if there's a topic you like to teach or a problem you like me to solve. Then lastly, like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.